In chapter 2 and 3, we talked about dynamics of particles. Now in chapter 5 and 6, we are going to talk about kinematics and dynamics of rigid bodies. So for a particle, when it's moving in a plane, we only need two variables to describe the location and to describe the location, velocity, and also acceleration of it. Like for example, using x and y in Cartesian coordinates, or r and theta in polar coordinate, and also a similar thing for normal tangential coordinate. But whenever we have a rigid body, let's say the rigid body is just moving in this plane, then it is not possible to describe the position and orientation of it with only two variables. For example, if I give you x and y of this point of this rigid body, you can rotate this, right? You can keep the x and y of this rigid body in this place, but you're free to rotate this rigid body. So you can change the orientation of it. In general, we need three variables to describe the position and orientation of the rigid body. Then after taking derivative of those variables, we can find the velocities of the rigid body. So the orientation is new here. We don't have orientation for a particle. A particle is a point, right? So the orientation of a particle has no meanings. But whenever we have a rigid body, in addition to position, we have orientation as well. To describe the orientation of a rigid body in plane, this is what we do. You need to consider any arbitrary line on this rigid body. This line can be this or something else, anything, any line on this rigid body, but it should be a fixed line on this. Then the angle between that rigid body and a fixed direction, like for example x direction, is going to be the direction of this rigid body. So this angle, if I call it theta, theta is going to show the direction of this rigid body. And if the rigid body rotates, for example, from here, if it rotates to another orientation, and let's say this AB line, now it is in a different location and orientation, then we are going to have a new orientation. If I call this theta 1, this one theta 2, theta 1 is the orientation at time 1. Theta 2 is going to be the orientation at the second time. Now, change in this orientation over time is going to be the angular velocity of the rigid body, which we show it with omega. So angular velocity which normally we show it with omega, is equal to change in the angle divided by time. And if these times are very close to each other, the change in the angle over time, we can show it with the differentiation. So change in the angle over time. It is very similar to what we had for velocity. So the definition of velocity was this: velocity is equal to ds dt. In velocity, we are taking derivative of the position with respect to time. In angular velocity, we take derivative of the angle or orientation over time. And similarly, we have a definition for acceleration. So omega is the angular velocity, and acceleration, we show it with alpha. And based on definition, alpha is equal to change in the angular velocity over time. And similarly, for movement of a particle, the definition of acceleration, linear acceleration, was derivative of the velocity over time. So these two equations are analogous with these two equations. And if you remember, for movement of a particle, these two are our essential equations. And if I divide them to each other, then dt is going to cancel out, and we came up with a new equation, which was time-independent equation. A ds is equal to v dv. And you saw it was very helpful in a lot of problems. We can do the same thing for these guys. If I divide them to each other, I'm going to find a time-independent equation. So similar to this one, I'm gonna have omega divided by alpha is equal to d theta divided by d omega. Then I'm gonna have omega d omega is equal to alpha d theta. Very similar to what we had over here, right? So in general, for rotation, we have these three general equations. Omega angular velocity is equal to d theta dt. Alpha is equal to d omega dt. And also the time independent equation is going to be alpha d theta is equal to omega d omega. These three equations are general and they are always true for a movement in a plane, for a rigid body. And if you remember, for linear movement, for movement of a particle on a line or also in a plane, if acceleration is constant in that movement, we can integrate these equations to find three algebraic equations, which are much easier to use than these differential equations. We can do exactly the same thing here, the same process. So I'm not going to write the details of it because it is exactly what we did for movement of a particle. So if acceleration is constant, which means angular acceleration is constant, then the integral of these equations are going to be this. For omega, we are going to have omega at any time is equal to initial omega plus alpha times t. Again, keep in mind, we are assuming alpha is constant. So if alpha is not constant, you are not allowed to use any of these algebraic equations. And also for the position of it, we are going to have theta is equal to theta 0 plus omega 0 times t plus 1/2 of alpha times t squared. In previous equations, we had s is equal to s naught plus v naught times t plus 1/2 of a times t squared, right? You see, we have exactly the same equations. And similarly, for time independent equation, if alpha is constant, we are going to have omega squared minus omega naught squared is equal to 2 times alpha times change in the angle. So these are the equations for rotation of a rigid body in plane. Now, to talk about the movement of a rigid body in plane, as I told you, we need three variables to explain the motion of it, right? But to make it a little bit easier at the beginning, I'm going to start by talking about rotation about a fixed axis. Or rotation about a fixed point. What's the meaning of that? Let's say our rigid body is pinned to the ground. So this rigid body is rotating about this point because it is pinned to the ground at that point, right? So if I ask you what is the velocity of this rigid body, then you should say velocity of what point? Because if the rigid body is rotating with angular velocity of omega, then the velocity of this point of the rigid body is going to be totally different than the velocity of this point or this point, right? Each point of the rigid body is going to have a totally different velocity. So velocity of a rigid body by itself doesn't have any meaning unless we specify a point on it. For example, velocity of the centroid of it. Or for example, velocity of this point of the rigid body is 0 because it is pinned to the ground, right? But the velocities of different points have some characteristics. For example, if you consider any point like this one, an arbitrary point on this rigid body, and while this rigid body is rotating about this fixed point O, if you track it, you're going to see this particle is moving on a circle, right? Because the distance between this point, if I call it A, for example, from O is not going to change. So the path of movement of that point is going to be a circle. And if you remember, for a movement on the circle, we know the velocity of this point is going to be tangent to the circle or perpendicular to the radius. And also velocity of A is going to be this distance times omega. So if I call this distance r, it's going to be r times omega. That's going to be the magnitude of the velocity of a random point like A with the distance of r from point O. I can also write this equation in a vector form. If I want to find the direction and also the magnitude in the same time for the velocity of A, I can write velocity of A is equal to omega cross r. To understand this equation, we need to I need to give you some introduction. First, omega. How can I show this omega in a vector form? Based on definition, omega, this angular velocity, is a vector which is perpendicular to this plane. So if I want to draw it, I need to draw a vector which is perpendicular to this plane. And if it's clockwise, the direction of that arrow, the vector, is going to be off the surface. So it's going to be something like this. It's going up. And it follows the right-hand rule. If you put your 4 fingers along the omega and try to rotate your fingers along the omega, your thumb is going to show the direction of vector omega. So the vector omega is perpendicular to this plane, and if omega is counterclockwise, it's going to be upward. And also r is this vector, right? Now, if you want to calculate omega cross r, based on right-hand rule, you need to put your fingers along omega upward, then rotate your 4 fingers toward the second vector, which is r. Then your thumb is going to show the direction of this result. If you do that, you're going to see your thumb is going to show this direction, because the result of this cross product must be perpendicular to omega and r. Look at this VA. It is perpendicular to omega, and also it is perpendicular to the omega vector, which is perpendicular to this plane. And also based on right-hand rule, omega is in the right direction. So this equation shows the actual velocity of the this point of the rigid body in a vector form. We can write a similar equation for acceleration. So if you remember, for any point which is rotating on a circle, acceleration has 2 components: tangential acceleration and also normal acceleration. If I show them with different colors, acceleration in the tangential direction and also acceleration in the normal direction. Acceleration of these points in the tangential direction is going to be equal to change in the velocity. If you remember, at is equal to v dot. And how v is changing, if you take a derivative of this, acceleration in the tangential direction is velocity dot, which means derivative of r times omega. R is not changing. R is going to be remain constant all the time, right? Because the distance between O and A is not changing. So v dot is going to be r times omega dot, and omega dot means alpha. So acceleration in the tangential direction is equal to r times alpha. And acceleration in the normal direction, if you remember, acceleration in the normal direction is velocity squared divided by r. And velocity is r omega. So an is going to be r omega squared divided by r, or it's going to be equal to r times omega squared. We can do the same thing here. Acceleration of A can be written in a vector form too. Acceleration of A is going to be equal to this r times alpha, similar what we had for the velocity, is going to be equal to alpha cross r. You can prove it yourself. Alpha, again, is a vector which is perpendicular to this plane. If alpha is in counterclockwise direction, based on right-hand rule, we are going to assume alpha is a vector which is perpendicular to this plane and it is outward. If alpha is clockwise, then the vector alpha is going to be to the plane. So alpha cross r is going to show the tangential part of the acceleration. And also, the normal acceleration, we can prove it's going to be equal to omega cross r in general. This is true for a planar movement and also for 3D movement. But we can prove, again, this is a simple thing that you can prove it yourself. This part of the acceleration, which has two cross products, and usually computation is a little bit expensive to do it, but mathematically we can show that omega cross r in plane is equal to negative omega squared times vector r. So omega squared is just a scalar, the magnitude of omega squared times the vector r. As you see, we can actually see it here too. Acceleration of omega is r omega squared. This is the magnitude of it, and the direction is in the negative r direction. And r omega squared in the negative r direction is going to be equal to this, right? So that's a very simple proof, right? I'm going to show the application of all of these equations in a lot of examples.